But for you today here on Math 115, we're doing a little bit on lines and planes and closest and points to a line, maybe intersection of a plane with another plane if we get to that. We'll show again what's going on. So the first question I want us to consider is the shortest distance from a point P that's given to you to the line with some vector equation, etc. right here. A couple of things you can tell from the equation of the line immediately is a point that it passes by, or this guy over here is a point that it passes by, and you can also tell the direction vector. It is the guy that gets multiplied by the scalar multiple here. That's always the direction vector. Okay, so knowing this, let's give a little bit of a sketch of the situation. You have some random point P out there in space, and another random line over here. The orientation doesn't matter. It really does not matter at all, by the way. I can make it like this without loss of generality. Nobody cares, honestly. So just make an arbitrary sketch here of the two. And then the direction vector, from this perspective that we have the line, again, it is arbitrary if that direction vector points up the line or down the line. Completely arbitrary, because if I shift the coordinates a little bit, both perspectives could be true. It's a matter of where you set the coordinates. So when there are no coordinates in your picture, it's arbitrary if it goes up or down. We don't know. Might as well choose it to go down then, you know, like something like this, let's say. That's the direction vector. And this point P0, it could be anywhere on this line. It could be directly below this P, which would make it the closest point. It could be here, here, here. I don't know where it is. Therefore, I'm just going to make a little bit of an assumption here. I'm going to make, I don't know, I'm going to say that it's here. I don't know where it is. It's arbitrary. Remember, without coordinates, things are arbitrary. So here's the thing. We're trying to find how far is the point P from the line. Like, what's the shortest distance? It's referring to this guy over here. Like, how big is this distance right now? Let's call it D for the time being. It's a size. So you go, okay, fair enough. How could I get it with concepts of projection? Well, one thing I notice is I can make use of this direction vector right here. If I had a vector connecting the 2 points here, if I had these two guys connected. So this direction vector that I have over here, I could project this line down here. Think of it, when you do projection, by the way, think of it like this. Like having a flashlight, like this, that shines some light, okay? The front of it is aligned with the side that you're projecting on. So again, for us, it would be looking like this, the front of it. It's aligned with the side that we're projecting on. And then, of course, the light shines, and it's projecting, again, the green line. So think of it as the shadow of the green line right now. If I have a flashlight like this up there, the shadow of this onto the blue over here would comprise the entirety of that blue. It would look, of course, like this. If I put it down, that would be the shadow. And that, of course, is what the projection is. So we would say, notation-wise, that this is proj of the vector that you are projecting, which is, of course, the vector between the 2 points. And the thing that you're projecting on would go in the subscript. It would look like this. So we're projecting on that vector D. Let me make sure that the recording is working. Okay. So, all right, you've got this. Now, if we were to close this triangle, I could draw you a vector that goes up again, maybe in color, what color do we have here? That's good, maybe pink. So I can draw you a color like this. Actually, let's make this pink because that annoys me, and make this green. So the pink connects the pink points, and this is the green one that finishes this triangle here. This green one over here is actually called perp. And it's an operator, just like projection. It would be the perpendicular distance where you're inputting the vector and its projection right here, like the place that you're projecting it on. So what this means is the perpendicular distance of P naught P onto the line defined by D. It's a big sentence, but that's what it means. The last thing to label here is P naught P. Feel free again to stop me at any time on Discord, like you can tell me if you have any questions. This is the situation. It would make sense here if you looked at the left of this picture that D is actually the size of that perp vector. Take a look at that, right? It's the size of it, if you look closely. The magnitude. So that means I gotta get this vector somehow. But then I notice that if I look at the red vector and the green vector, they're adding head to tail to get me the pink vector. Literally, head to tail, as you can see, to get me the resultant, which is the pink vector. I could say, P naught P is equal to the sum of the other two. The proj, and of course, the perp. Like this. And again, let me color code everything nicely. So the proj of P naught P and the perp of P naught P onto vector D. So if I wanted, of course, here Chavi to isolate for the perp, I could get it by having this P naught P vector, okay, on the other side, and then subtract the projection. Just move this on the other side, basically, the projection on the pink side. That's it. That's another thing solved. But of course, this requires us to know these two. So we gotta go and get them. You gotta get P naught P as a vector, and you gotta get over here the proj. Okay, but that's not a big deal. We can get these things. Let's start with a P naught P. Every time you're trying to find a vector again between 2 points, you do final minus initial. That's all. So P minus P naught. And you know these points, The given point for you has been given, and the P naught, we've identified it on the line. So that's P, 1, negative 1, 3, and 2. And P naught, which is 1, negative 5, and negative 2. We do again addition component by component and get ourselves, 1 minus 1, 1 minus 1 minus 1 is negative 2. 3 plus 5 is 8. 2 plus 2 is 4. Done with that one. Let me make sure the numbers are okay. 1 minus 1 minus 2, 3 plus 5, 8, 2 plus 2, 4. Okay, that gets rid of P naught P. Then we need the projection, which has a specific formula involving the dot product. D always goes at the end here, the D vector. And we also scale by its magnitude here. We scale by its magnitude squared. The dot product between these two guys. The order doesn't matter because you don't have complex components. So you can write the dot product whatever order you want here. Because you have real numbers in the components. If you didn't, we would have to do a little bit of a talk about that. Okay, so all in all, you have the dot product between negative 2, 8, and 4. Dotted with, we're going to put the D vector here in a second. Okay. So the D vector was negative 2, 2, and 1. Let's get it in. Negative 2, 2, and 1. Negative 2, 2, and 1. And the size of it squared, it won't be the square root because you're squaring. The square root will go away. So you're basically adding the square of the components. Negative 2 squared plus 2 squared plus 1 squared. Done. And then you evaluate. The magnitude here is 4 plus 1. That's 9. The vector at the front stays the same. Negative 2, 2, and 1. And as for the dot product, negative 2 times negative 2 is 4. 8 times 2 is 16. 4 times 1 is 4. That is in total 24. There you go. That's the projection. Now we can simplify this a little bit, and I really mean a little bit. Everything is base 9 here. We can't get away from that problem. So you end up with negative 48 over 9, 48 over 9, and 24 over 9. All right, that's the projection vector. Nice. So what do I do with this now? I have to do a little bit of algebra. So I have the projection. In fact, that should be going in reverse. Like, these should happen first. We've reversed engineered the problem, right? So these should be going first. Then I should be figuring out what the perp is right after. And then I should do this at the very end. So kind of reverse engineered what we need to do here. So to get the perpendicular, we got to get the P naught P and subtract this projection. Let's get it done. Really quickly, it's just numbers. Boom, boom. All right, taketh away. Let's make this red so it stands out with projection. You got to make everything base 9 here, unfortunately, for this to work. So multiply everything by 9 over 9. Negative 2 times 9 is negative 18. 8 times 9 is 72. 4 times 9 is 36. And then we got plus 48 over 9 minus 48 over 9. And then minus 24 over 9. There we go. A little bit of fraction work. And you get yourself, what is that? 48 minus 18, 30. Sorry, 40, 30 over 9 is the first component. 72 minus 48, that's 64, 24 over 9. 36 minus 24 is 32, 12 over 9. Nice. So at the end of the day, that's the perp that we just found over here. We just got to find its magnitude. And to find its magnitude, take the square root of the components squared. And that would end that question. Well, the part of that question, I guess. This finds the distance in whatever units you're using in this question. So a little bit rough here to get that distance, whatever it is. I'm not going to actually simplify this because that's going to take forever. It is what it is. You could do a few things. 9 squared is 81. If you square root it, it's 9. You can pull it outside the whole thing. But then inside, you get 30 squared plus 24 squared. You need the calculator for that. 30 squared is 900. Plus 24 squared. Plus 12 squared, which is 144. You get 1620. So 1620 over 9. I'm not going to root that. I don't know if that's going to come out nice. 1620 over 9. Whatever that comes out to, Chavi. We don't really care. That's your answer. That's the minimum distance. And it's the minimum because of the way perp works. It gives you the perpendicular distance between that vector and the other vector. Perpendicular distance means minimum distance. Anytime you have two objects, let's say there's a point there and a point there, and a line like this, okay? And I want to find where, like, how far is this point from this line? You can see automatically when I ask that question, I'm defining a perpendicular line. So the perp always gives that minimum distance no matter what situation here I'm in, because by its nature, it connects things perpendicularly. What do you think about this? Was this okay? The structure here, was it okay how we did it? I'll put it all in perspective there. Let me know. I can also pause the recording for now. So fair question, we did a closest distance of a point to a line. What if it was a plane? Fair enough. So these are the two vectors that define the plane. Like, you can use them to actually define your plane. Let's make the plane, I don't know, maybe like a shape like this or something. Doesn't need to be fancy again. Let's make it like this. And put the point somewhere up there now. The P that you were given, let's put it up there. Once again, this little guy right here, you're seeing right there, is actually a point contained by that plane, P0. So the others are just direction vectors, that we can use to construct any vector on that plane. So basically what we're saying with D1 and D2, if I give you a vector like this, you can always scale D1 and D2. You can always scale them to get yourself that vector of interest. Any vector on the plane can be described as some kind of linear combination of D1 and D2. The sum of them. Some kind of linear combination. That's what the D1 and D2 do for you. Okay, so let's say that D2 is a little longer, maybe like this. Hold on, I'll give you a good visual. It doesn't matter how you draw them, because again, we don't know how they look like in an arbitrary coordinate system. But I'm going to guess that they look like this, whatever. Now these two, we learned last time before you went to write your quiz how to do cross products. And when you do the cross products between two vectors, you get a vector that's normal to both of them. So I could theoretically, right now, take these guys, put them right under. You can move these around, okay, without loss of generality. You can parallel transport vectors in linear algebra without losing generality. So I'll move them right under the point P, and I will generate again a normal vector. Boom, like this. That will be your normal from the two. And the normal will be the direction vector to some line. If you see here, it will be the direction vector to some line that goes straight through P. Check this out, like this guy over here. It goes straight through that. Fair enough. Now what else do we know? P0 is a point that is somewhere on the plane. It doesn't matter where you put it. But put it somewhere nice so we have a lot of space to work with. I'll put it probably like over here. Now, okay, the concepts that we learned for the lines kind of follow through here, but not exactly. You have to do something different, obviously, here. So I still would connect P0 to P, just like I did previously, like this, and get the vector P0 P. Like that. But then you go, projection. If I project right now, where do I project on? Like, if I do the same that I did with the line earlier, the projection should be somewhere on the plane. But should I project along D1 right now? Should I project along D2 right now? That vector? That's kind of arbitrary all of a sudden. And I don't think it would help me much, to be honest with you, if I did that kind of projection. There are infinite vectors on this plane that I could project on right now. Literally. infinite. Maybe this is not a great idea, is what I'm trying to say. But, what if I decided instead to project along the line defined by the normal vector? I can do that. Before, we did not have a vector like this. If we did, we could have gotten away with just finding the size of this projection. But we don't have that up here, you see? We don't have that vector given to us. The D is on that line. It's not along the green, okay? It's not along the green, but now it is along the green. So it's a little bit different in a way. So I actually will project this, my flashlight will shine light in this direction and project this again on the yellow line, as you can see. That's what I'm going to do. So I'm going to cast the shadow. Let's keep the coloring that I had originally. Make this blue, the normal. I'm going to cast the shadow, which is going to be the projection right here. There it is. All right, let me write it down. Who are we projecting? We are projecting, of course, P not P on the vector N, which is blue actually. Okay, let's go. So, how do I find N? I need N to begin with, and then I need to find the projection, and then I need to find, the size of it. So there's a few things I gotta do. I gotta figure out P not P. I gotta figure out the normal, the blue guy. Let's start with P not P. Easy. Final point minus original point. So, let's do it quickly here. Put it all down. P is supposed to be the point that we had earlier, which was negative 1, 3, and 2 up there. Negative 1, 3, and 2. Okay. And P0 is supposed to be the one that we have on the plane, which is, of course, the 1, 1, negative 1. All right. We do the subtraction. What do we get? We get negative 1 minus 1 is negative 2. 3 minus 1 is 2. 2 plus 1 is 3. Good stuff. Out of the way. N, we said, is supposed to be the cross product between D1 and D2. Now, I've taught you last time how to do this in terms of a determinant. I still insist you try it like this. So we line everything up. We line the x hat, the y hat, and the z hat up here. Then we line the components of D1 and D2. 1, 2, and negative 3. 2, negative 2, and 2. Okay. So it begs the question, I know what you're wondering here. What if I labeled by accident this one as D1 and this one as D2? George, what would happen if I did that? Can you take a guess on Discord what would happen if I messed up the order here? Quote unquote messed up the order? What do you think you would get? Any ideas? Oh, I'm not torturing you too much. It would be the negative of the normal vector that we want. Not the one that we want. There is no want, okay? There is no want. There is a line that you're interested here. So a lot of people are focusing on the normal vector, and they're forgetting that we can define the line that it belongs on. Whether we take the normal that's oriented up or down, it doesn't matter. Both of these act as direction vectors for that yellow line. So it doesn't matter if you switch the order or not. the math will still be the same. Coincidentally, of course. So you care about defining this yellow line. Whether you get the positive, quote unquote, or negative normal, it doesn't matter. Both of them are direction vectors to the yellow line. Things in linear algebra are not exactly unique. And this is an idea that people struggle with because they think that because the professor wrote this, that's the only way that you can write the plane. No, it's not. This was one of infinite points that belong on the plane right now. I could generate you 100 more just by putting in here values for R and values for S. If I put values of R and S in there, I can get you another point that belongs on the plane right now. And people forget that, right? And then the new point that I find you, if it's easier for some reason, I don't know, it's 0, 0, 0 that I found. If it's a nice, easy point, I'm like, okay, why am I carrying this? I will replace this with 0, 0, 0 and get it out of there. So this freedom scares people in linear algebra. Until you understand it, you're going to be out of the course, but I will keep emphasizing it. Similarly, with the direction vectors, again, those are not unique. You can clearly see that I could factor right now over here. I could factor outside of 1/2 and hide it, tuck it away inside this R. Remember, R is a real number. I can tuck the 1/2 into the R and nothing happens, leaving me behind with 1/2, 1, and 3, and sorry, negative 3 over 2. That's still legit. Still a legit way of writing the equation and the direction vector. And yes, everything would still work out when you do the cross product for the normal. Same. And that again, people have a very hard time coming across and accepting, right? So I'm emphasizing that you have a lot of freedom here for writing out things, especially if they're getting multiplied by random constants. So the order doesn't matter, what you call D1 and D2, right? As long as you do the cross product correctly, you're good to go. Let's do the cross product. All right, so we got ourselves here 1, 2, and negative 3, 2, negative 2, and 2. I'll do it the way that I taught you. Unfortunately, I can't have you speak it out, but I'll do it the way that I taught you. So remember, I put a matrix here beside this with signs alternating. So when we start, we go along this line. First guy is this. So we have a plus x hat. And then the determinant, which we also symbolize like this. I need to teach you this notation too for later in the class. Determinant, we symbolize it as the absolute value of the matrix as well. Okay, you'll see it a lot. Just to save ourselves from writing det all the time. So what are you left with? This, right? So 2, negative 3, negative 2, and 2. Done and done. Moving on to the next. So this one is a negative y hat, and then the determinant of 1, negative 3, 2, and 2. And then finally, to show you here, this one is a plus. So plus z hat, the determinant of 1 and 2, and 2 and negative 2. The 2 by 2 determinants, I taught you that you just do the subtraction of the product of the diagonals. 2 times 2 is 4, minus that product's the 6. 4 minus 6 is negative 2. So negative 2 is the x hat component right now. What about the y component? Let's see. 1 times 2 is 2. This amounts to negative 6, and we're subtracting it. So it's positive 6 plus 2 is 8. But then you have a negative here, so it's negative 8. Boom, boom, boom. And then the last one again, negative 2. This amounts to 4, and we're subtracting it. And then we have negative 6 overall. There's your normal. Out of the way. Done and done. Okay, nicely carried out. So we got the two pieces that were long. Now let's get the easier ones. We said we're going to project the P naught P onto the line defined by the normal. So I'm looking to find this projection. So I'm just going to copy that with the colors. And we know how to write out the projection, the formula for it. The normal will go to the end, and we will scale by its magnitude squared at the bottom. At the top, we're going to have the dot product with P naught P dotted with N. Again, the order of dot products doesn't matter unless we have complex numbers. The order of cross products does matter. It flips the sign. All right, here we go. Get the P naught P in here, dotted with N, which I have right above me there. I can just copy it right now. It is -2, -8, and -6. And then we put it at the front as well, -2, -8, and -6. Nice. And then we have underneath the size squared. So no square roots again. Just take the components of n and add their squares together. Like this. P naught P is -2, 2, and 3. Let's get it. All right, close to the end here. We got the denominator reading 4. That's 64, and that's 36. So that together here is 70. That's 100. 104. Okay, the top part, as we do it, is 4 minus 16. Minus 3 times 6 is 18. Minus, so 4, -16, and -18. Okay. All together here, that's -20. Sorry, -12. -20, -30. Okay. Yeah, because that's -34 plus 4 is -30. Okay. I don't like these numbers, but what can you do? It's an arbitrary question. Okay, so at the end of the day, that's the projection of vector. And the distance, we said, is just the size of it. You can see it from the diagram, right? The size of the projection vector is the distance, shortest distance. So I evaluate the magnitude of proj in this one. It's not the magnitude of the perp like on the other one that we just did. It's the proj. Not a big deal, just being careful. And that is the square root of -30 over 104 squared times -2 squared plus -8 squared, blah, blah, blah. As we put the components in, all square rooted. At the end of the day, that's 108. I guess you can pull this outside the square root and write it as 30 over 104 because it's a square getting square rooted, as you can see here. And then the inside becomes, quite obviously here, the square root of 104 itself. So all in all, you get 30 over root 104. And that would be D. That's it. So hopefully, again, this makes sense. It's a little bit of a different geometry setup, but same principles apply, you know? Find a vector whose magnitude could get you that shortest distance. It just so happens that it's the projection on N here instead of the perp on D before. What do we think? Did we follow along? Yes. Okay. I think that yes came right now. All right. Perfect, perfect. Let me pause one sec. So if you are doing intersections now, actually would be a good idea to stop the recording and pick it up on the next topic. Hold on a sec.